this time I expect you would have at least attempted the MCQ portions, right? So let's go ahead and solve these problems. So this is sheet titled Kinematics Revision. So we have the first problem, modified projectile motion. Particle launched from A at an angle theta with a velocity u, and there is an additional acceleration g tan theta to the left, which means in the horizontal direction the acceleration is not zero. So the velocity in the horizontal direction will not remain constant. Alright. Now what we want to be able to find is, by the time the particle falls on the x-axis, whether it's going to fall at A or to the right of A or to the left of A. That's what. Now a horizontal acceleration will not disturb the total time of flight, because the total time of flight is the initial vertical velocity twice the initial vertical velocity by the downward g, right? That's the total time of flight. So the total time of flight remains the same, which is like 2 times the initial vertical velocity, in this case 2u cos theta divided by g. That's the total time of flight, right? In this time of flight, let's find out the horizontal accelerate, the horizontal displacement in the x direction in this time, subject to a negative acceleration g tan theta leftwards. That's going to be initial velocity in the horizontal direction is u sin theta into the time t, which is 2u cos theta by g ut minus half a, which is g tan theta, into t squared, which is 4u squared cos squared theta by g squared. Yes or no? Do you realize that this turns out to be 0? If it turns out to be 0, means by the time it falls flat on ground, it must be at A. So that means it returns to A. In a full time period, in a full time of flight t, it returns to A. The particle reaches A on the ground, right? Alright, a particle starts from O with an initial velocity u, having an acceleration in the negative x direction. This is the plus x direction, and that's the negative x direction with an acceleration a. If t is the time at which its velocity changes, means at the instant of time t, its velocity becomes 0. So that then, under the influence of a leftward acceleration, the direction of motion changes, right? So now, in time t, let's say it reaches a point m. It reaches a point m. And very clearly, this distance OM would be u squared by 2a. U squared by 2a is this distance. Yes or no? Right? Because the velocity here becomes 0. Now, there is an instant of time t. There is an instant of time t when the particle is, let's say, at A. There is an instant of time t when the particle is at A. And OA then would be up minus half ap squared. Now from this instant the particle turns back, it starts to move like this, and from the point M, there is an instant of time p plus 1 when the particle arrives at P. There is an instant of time p plus 1 when the particle arrives at B. Now, we want to be able to find this total distance. We want to be able to find the total distance in the p plus 1th instant. In the p plus 1th instant, very clearly, the total distance in the p plus 1th instant would be the distance from A to B. An plus Nb would be the total distance. An, as you can readily see, is u squared by 2a minus up minus half ap squared. That's the distance A. And from N to B, from 0 velocity with an acceleration a, in time t plus 1 minus t seconds, and p plus 1 minus t seconds, it covers half of a into p plus 1 minus t. So that's the distance it covers in the p plus 1th second. In the p plus 1th second, that's the distance that it covers. Yes, sir. Right? Got me? Can I write this off? There is a platform P that's moving to the right with a velocity v1. And there is a platform Q which is inclined at an angle theta with the horizontal, and it moves with a velocity v2. It moves with a velocity v2. The rod OAB passes through a hole in the plate P. There is a rod OAB that passes through a point through a hole in the plate P, and it is fixed on the plate Q. The rod OAB remains vertical while P and Q are moving as shown. We want to be able to find the relative velocity of the point O with respect to the plate P. Now, evidently, for this rod to remain vertical, what's important is that the displacement of V horizontally must be equal to displacement of A horizontally. Yes or no? In a given time, the extent to which A gets displaced to the right must be the extent to which B gets displaced right. That would cause the rod to remain vertical. At all times. Now, which means if I resolve the velocity of the platform P in the horizontal and vertical direction, then I have like a v2 cos theta horizontal and v2 sin theta vertical. Yes or no? Very clearly, the horizontal velocity of A must be equal to horizontal velocity of B, so that the rod remains vertical, which means v2 cos theta must be equal to v1. That must be a condition. Now, as far as O is concerned, well, O, A and B, all of them have the same horizontal velocity. The points O, A and B have the same horizontal velocity, so O for sure has the same horizontal velocity as this platform P, which is v1 to the right. But in addition, it has the same vertical velocity as V. Keeping rigid body considerations in mind, it has the same vertical velocity as B, which is like v2 sin theta. That means if you are an observer on this platform, then you will not witness the common v1 to the right. All that you will see on O is v2 sin theta. So the relative velocity of O with respect to the observer P, that is the platform P, is going to be v2 sin theta. Got me? Yes or no? Right? Shall we proceed? There are 2 points P and Q, path of a projectile. There is a point P, VP, and there is a point Q where the velocity is VQ, such that the velocity VP in direction is perpendicular to the velocity VQ, right? We want to and also alpha is the angle that VP makes with the horizontal. This angle is alpha. So since VP is perpendicular to VQ, what VP does to the horizontal is what VQ does to the vertical, right? So that means VQ must be making an angle alpha with the vertical, and the horizontal velocity from VP must be the same as the horizontal velocity from VQ. Why? Because there is no acceleration in the horizontal direction, right? Which means VP cos alpha must be equal to VQ sin alpha, which causes cot alpha to become VQ by VP. Yes or no? Right? Does it make sense? Shall I move? Problem 5. Loaded bucket of a crane achieves a maximum velocity Vm in some time at a uniform rate and then takes half of this time to stop at a uniform rate after application of brakes. Alright. So the velocity time graph would be, in a certain time it reaches a maximum velocity at a uniform rate, means v versus t must have been a straight line, constant acceleration because it's a uniform rate, and then it retards faster. It retards faster because it takes less time to have its velocity reduced to 0. But again, it retards uniformly, and this is what happens. Now, the time difference between the instance when half of the maximum velocity is achieved is t seconds. We want to be able to find the displacement of the bucket. Displacement of the bucket means the area under the velocity time graph will be the displacement of the bucket, right? And realize that half of the maximum velocity is attained at 2 instants of time. This is 1 instant of time when you attain a Vm by 2, and there is yet another instant when you attain a Vm by 2. These are 2 instants when half the maximum velocity is attained, and the interval between these 2 instants is t seconds. Right? Now, very easy to see. Do you realize that if OB is T1, then BC will also be T1, right? Similar triangles, isn't it? Similarly, if CD is T2, DA will also be T2. You see that? If you don't understand this, I'll explain. I hope all of you understand this, no? I mean, this length is the same as this length, so this length will be the same as, right? Because these angles are the same. So if this is T1, this must also be T1. Similarly, if this is T2, this must also be T2, and this must be T2 there, right? Yes or no? Now, evidently, T is T1 plus T2. T is T1 plus T2. Whereas the total time is T1 plus T2 is the total time. Do you realize that? The total time from O to A is 2 times T1 plus T2, right? Which is like 2T is the total time of motion. So then the area of this triangle, which is half of Vm into this length, which is 2T into 2T. So which is Vm into T. That must be the displacement. That must be the displacement. How about? Yeah. Shall we proceed? A particle starts to move a distance of 20 meters on a straight line to achieve a maximum acceleration, A max, of 10 meters per second squared at such a rate that its velocity at s equal to 20 is 10 root pi meters per second. Velocity at s equal to 20 is 10 root pi meters per second, with the acceleration at s equal to 20 being 0. So it starts from 0 acceleration and runs into 0 acceleration with a maximum acceleration, which means you would expect the acceleration displacement graph. Well, it starts from 0 it becomes 0. And somewhere between, and this is s equal to 20, s equal to 0. And somewhere it's going to attain a maximum acceleration of 10 meters per second square. It's the maximum acceleration that it would attain. Right? Now, acceleration is v dv ds. Acceleration is v dv ds. Which means very clearly integral v dv is integral a ds. S starts from 0 to s. Yes or no? What is the right hand side? The right hand side is the area under the a versus s graph from 0 to this end. From 0 to this end. Right? So this is area under the a's graph. This is the area under the a's graph. Yes or no? And v dv means it starts from 0 and goes to a maximum velocity v at s equal to 20. At s equal to 20. Which means v squared by 2 is this. The area under the graph must be the final square of the final velocity by 2. That must be the area under the a's graph. The final velocity squared by 2 and the final velocity squared is 10 root pi. So this is like 100 pi by 2, which is 50 pi square units must be the area under the a's graph. 50 pi square units. Means, you know, the moment you get something like a pi, you would think of a circle, isn't it? Your first impression would be a circle right away. And then you don't have to make any calculation. You would readily mark B, but then, you know, if you still want to check, look at this circle. 10, 10, area of the circle, half pi r square. Area of the circle, half pi r square. So half pi into 100, which is 50 pi. So it matches. So option B. In an exam, of course, you won't do this calculation. The moment it's a pi, you know the rest of the curves are unlikely to give you a pi. Then you go with the sweetie pi here, right? You might have forgotten very quickly. If there is this particle launched along an inclined plane, right? Say this angle is alpha and this angle is beta, this angle is alpha, this angle is beta, then you have like a u cos alpha along the plane and u sin alpha perpendicular to the plane, right? And g is like a g cos beta perpendicular to the plane and g sin beta parallel to the plane. You remember all of this, right? And the total time of flight would be, let's say this is the x direction and this is the y direction. The total time of flight would be when y becomes 0, right? Right, the displacement in the y direction as a function of time starting from t equal to 0 is given by what? Initial velocity in the y direction, which is u sin alpha into t minus half g sin beta into t squared, which must be 0 at a total time of flight. G cos beta, I'm so sorry, this is g cos beta. This will give me the total time of flight, which is like t equal to 2u sin alpha by g cos beta is the total time of flight, right? And O to A, that's the range. This is some and beta. This is u. All that you need to do is take the component of u in this direction, which is u cos alpha plus beta. U cos alpha plus beta acting for t seconds would cause a horizontal displacement of this much. Acting for t seconds will cause a horizontal displacement this much, and the whole divided by sec cos alpha will give you the range OA, will give you the range OA along the plane, right? Do you remember all of this, right? So now, this is the next problem. We have this particle. It goes from O to B. That's the range, right? And the total time of flight, as you can see, is like 2u sine theta by g cos theta. That's the total time of flight. Yes or no? 2u sine theta by g cos theta is the total time of flight. How about it, right? And its displacement OC in the total time of flight would be this into u cos 2 theta is the displacement in equal to the total time of flight. That is its displacement along OC. That is its displacement along OC, right? Because the velocity along OC is u cos 2 theta. Acting for t seconds will give me OC, and then OC divided by cos theta will OB. So this divided by cos theta will give me OB. Yes or no? Right? And this OB is given to be 2u squared tan theta by g root. Yes or no? Right? And this gives us, so we have 2u squared getting cancelled, g getting cancelled, and then we have like a cos tan theta getting cancelled, a cos theta remaining behind. So we have like a cos 2 theta by cos theta as 1 by root 3. Yes or no? So think of it as half divided by, you don't have to calculate. I mean, just by inspection, this is like half divided by root 3 by 2. So you would expect theta to be 30 degrees, right? Half divided by root 3 by 2 would give me 1 by root 3. And that's going to give you theta equal to 30 degrees, right? Right? Alright, so we have this platform P moving to the right with a velocity Vp. Moving to the right with a velocity Vp. Alright. And there is this hemispherical shell. And this rod, which passes through a hole in the platform, touches the shell at B. Right? So, when the rod just moves to the right, the point A just moves horizontally, the point B not only moves horizontally but also descends. Because of the curvature of the shell, it also descends. So the point B not only has a horizontal velocity but also has a vertical displacement and therefore a vertical velocity. Now what we want to be able to find is the velocity of the point B with respect to the platform. Now, it's also given that the rod remains vertical. The rod remains vertical means at any given instant, the horizontal velocity of P must be equal to horizontal velocity of V for the rod to remain vertical. That means for sure, B has a horizontal velocity Vp, has a horizontal velocity Vp, right? P has a horizontal velocity Vp, clear? And not only that, the net velocity of B must be along the tangent, right? So this is theta, this is theta. So if I complete this rectangle, then do you realize that this must be the vertical velocity of B, this must be the vertical velocity of B, and very clearly vertical velocity by Vp is tan theta. So the vertical velocity of B must be Vp tan theta, yes or no? The vertical velocity of B, which is V naught, must be Vp tan theta, And this is the only additional velocity that it has compared to the platform, because this Vp and this Vp are the same between the platform and the point B. So the relative motion of V with respect to the platform is Vp tan theta downward. Downward. And what's the net velocity of the point B? Root Vp squared plus Vp squared tan square theta. That is Vp sec theta. Vp sec theta would be the net velocity of the point B. Right? Samir, You got me? Okay. Realize that the maximum height is proportional to the square of the initial vertical velocity. Yes or no? The maximum height is proportional to the square of the initial vertical velocity. Right? Maximum height is given by uy squared by 2g. It's given by uy squared by, right? And the total time of flight is proportional to uy squared, is proportional to uy. The total time of flight is proportional to uy. 2 times uy by g is the total time of flight, right? So uy is proportional to capital T. That means h max is proportional to t squared. H max is proportional to square of the total time of flight, because uy is proportional to the total time of flight. uy is proportional to the total time of flight. So h max is proportional to the total time of flight, which means I can say that h2 by h1, that means the maximum height reached by 2 divided by maximum height reached by 1, which is 1 by 2, 1 by 2, that must be total time of flight of 2 divided by total time of flight 1. Yes or no? h2 t2 squared by t1 squared proportional to t2 squared by t1 squared, which means the total time of flight t1 is root 2 times the total time of flight t2. The total time of flight t1 is root 2 times the total time of flight t2. Now realize that the range is given by what? The range is given by the in horizontal velocity ux into the time of flight t. That's the range. Now, so what if one time of flight is root 2 times the other time of flight? One ux can be 1 by root 2 times the other ux. That means it's possible that despite different t's, ux into t could have been the same. Always maneuver their ux in a manner that ux into t is the same. So what if t is different? I still have ground to play on ux. So I could have still caused the product ux into t to be the same. So it's a possibility that the ranges are the same. It's a possibility that the two ranges are the same. One t is root 2 times the other t, agreed, but the ux could be 1 by root 2 times the other ux. In which case, the product ux into t could have been the same for the two motions. Therefore, right? So R1 equal to R2 is a possibility. Very clearly, when it says R2 is 2 times R1, that's rubbish. No. Ranges can't be the same. No, of course, they can be the same. So option B, option B. Shall we proceed? So we have a system of two fixed pulleys and one movable pulley connected to two objects. One has an instant of time t and acceleration 12 t squared upwards. The other one has an acceleration 6 t downwards. Right? Now, again, if you go back to the string constraints which I taught to you, then at the same instant, I can find the acceleration of c. I can find the acceleration of c. Let me assume that the acceleration of c is a downwards at this instant of time. Right? I mark the nodes. This point is like 12 t squared. This is like 0. This is like 0. This is like a downwards. This point is like a downwards. This point is 0. This point is 0. And this point, of course, is 60 downwards. So I traverse the string from this end all the way to B. Right? So when I do that, then I get like a 0 minus 12 t squared. That's keeping in mind the constancy of string length. 0 minus 12 t squared plus a minus 0 plus 0 minus minus a, 0 minus minus a. I'm assuming you have not forgotten all of this. Plus 60 minus 0 plus 60 minus 0 equal to 0. Those of you who have not been in my class might want to see me at some other time. you know what exactly I have done here. I'll keep them distinct constraints separately. But this gives me like A equals 6t squared minus 3t. Yes or no? This is what I get for A, the acceleration of C as a function of time, 6t squared minus 3t. And this could be written as dB/dt. So this would give me an opportunity to calculate V as a function of T. Right? So when I integrate, I get V equals, right, T cube by 3. So 2t cube minus 3t squared by 2 plus a constant of integration. But at t equal to 0, V is 0. Why? Because the system started from rest. So that would give me C equal to 0. That would give me C equal to 0. So this is like t squared into 2t minus 3 by 2. So the velocity would be 0 at t equal to 0 and at t equal to 3 by 4. At t equal to 3 by 4. T equal to 3 by 4 is the instant of interest when the velocity. So the element C comes momentarily to rest. Its velocity becomes 0 doesn't mean its acceleration will become 0. Right? Its acceleration is still non-zero, but its velocity will momentarily become 0. It's only when acceleration and velocity simultaneously become 0 that the particle will come to rest permanently. Right? So t equal to 3 by 4 when it comes to rest momentarily. Alright, so we have this particle which is launched with the velocity u making an angle alpha with the horizontal. Now when the particle moves, its horizontal velocity remains the same and its vertical velocity decreases. The resultant would acquire affinity towards the horizontal, so the angle tilts, it becomes smaller, right? Because the net velocity comes closer to the horizontal velocity. In a time t equal to u by g root 3, the angle decreases by 30 degrees. That means alpha minus beta is 30 degrees. And we are seeking the value of alpha here. We are seeking alpha from these constants. Now very simple. Look, at both these instances, the horizontal velocity is the same, right? Which means u cos alpha must be v cos beta. How about it? U cos alpha must be v cos beta. Now, the vertical velocity very clearly, v sin beta, the vertical velocity must have come out of u sin alpha depleting. U sin alpha minus gt must be v sin beta, right? And then when I divide, then I have sin beta by cos beta equals u sin alpha minus gt by u cos alpha, right? And then notice that I could have had sin alpha cos beta and then minus sin beta cos alpha. They could be consolidated. So sin alpha cos beta, so that gives me u sin alpha minus beta equals gt cos beta. How about it? I hope you realize what I did. Cross multiplied and then u sin alpha cos beta minus u cos alpha sin beta is u sin alpha minus beta is gt cos beta. Collecting terms, right? But g into t is u by root 3. So this g into t I can replace by u by root 3. And alpha minus beta is 30 degrees. Alpha minus beta is 30 degrees and sine 30 degrees is half. So u by 2. So that gives me cos beta as root 3 by 2, or beta must be 30 degrees. Beta must be 30 degrees and therefore alpha must be 60. Alpha must be 60 degrees. Yes or no? Fair enough, right? Shall we proceed? Passage 1. A shot is fired from a point A horizontally with a velocity u equals 10 root 3 meters per second. This is of mass m. Another shot of twice the mass fired from B at an angle of 60 degrees with the horizontal. This is the horizontal. With the same velocity u, it's fired at an angle of 60 degrees. And the two shots collide in air. Right? Now, A and B are joined and we want to be able to find the angle theta. Hey, look. What we do is, we make A the observer. That means freeze A. A is made the observer. That means A is frozen in freeze. Then the velocity of V would be the velocity of V minus the velocity of V. Then the initial velocity of V will not be velocity of V. It will be velocity of V minus the velocity of A. Velocity of V is like this, and this was the velocity of A. So negative of the velocity of A will be like this. Negative of the velocity of A will be horizontally leftwards. This would be negative of the velocity of A. That means velocity of V, and this is negative of velocity of A. This must be velocity of V with respect to A. This must be velocity of, if I add this u and this u, this will give me velocity of V as seen by V, right, at the initial limit. Now, they have the same accelerations, g downwards. So, their relative acceleration is 0. Therefore, their relative velocity must be constant. That means, if at this instant of time, A perceives B to be having a velocity which is the resultant of this u and this u, then at all instants of time, A will perceive the same velocity in B, right? And which means the resultant of these two velocities is the velocity of B with respect to A all times. That means B approaches A with a constant velocity. Now, it's also given that in addition to this, there is a collision occurring between B and A. There is a collision occurring between B and A, which means if a collision has to occur between B and A, realize that the resultant velocity of B with respect to A must be along BA. That means the resultant of this u and this u must be along BA here, right? Now, evidently then, since these two vectors, u units and u units, they are equal in magnitude, their resultant must be equally inclined to both. And the total angle here is 60 degrees. That's given. This u makes an angle 60 degrees with the horizontal. That means this must be 30 degrees and this must be 30 degrees, yes or no? Does it make sense to you or not? Right? Which means if this is 30 degrees, theta must also be 30 degrees, alternate angle. Here? Sound alright? Now, if height of B is 10 meters more than A, we want to be able to find the time taken for the collision. Okay. In the equivalent situation, this is the equivalent situation. By the time B bumps into A, which is the resultant of this u and this u. Right? The vertical displacement of B as seen by A must be 10 meters. The vertical displacement of B as seen by A, where it bumps into A, must be 10 meters. And that's at the behest of the vertical component of the velocity of B. The vertical component, look, the vertical component, this U has no vertical component. This has a vertical horizontal component U cos 60 and a vertical U sin 60. That means U sin 60 is instrumental in providing a vertical displacement of 10 meters when collision occurs. Right? Right? And this U sin 60 degrees remains constant with respect to A. Right? Because this is an equivalent situation. Relative acceleration is 0. Now the time taken for a vertical displacement of 10 meters then is 10 meters divided by the vertical velocity that caused it. The vertical velocity that caused it is U sin 60 degrees, yes or no? That's the vertical velocity that caused it. Right? And U is 10 root 3. U is 10 root 3. So 10 by 10 root 3 into root 3 by 2. So that makes it 2 by 3. 2/3 of a second is what it takes for B to bump into A. Right? Is there a confusion? No. Find the horizontal direction. Find the direction of velocity of the combined mass subsequent to collision. You have a confusion, no? I know. Find the direction of the velocity of the combined mass after collision. After collision. Realize that one mass is twice the other mass, right? And when they collide, or rather, their horizontal velocities at the instant of collision will be the same, right? So A at the instant of collision is U like this, and B at the only the horizontal velocity at the instant of collision is U cos 60 degrees independently. Their absolute velocity that's seen by the ground is going to be U cos 60 degrees like this. Their horizontal velocities remain the same at all times, and so also the instant of collision. But the mass of A is m and the mass of B is 2m. So just before collision, you realize that A has a linear momentum mu to the right, B has a linear momentum mu to the left. That means their net linear momentum horizontally is 0 before collision. And in the horizontal direction, there is no external force acting on the system. Therefore, the combined mass will have no net horizontal linear momentum post collision. Therefore, the combined mass will fall vertically. The combined mass is bound to fall vertically. See, the net linear momentum before collision is 0. So the net linear momentum after collision must be 0. Horizontal. So that means in the horizontal direction there will be no motion of the combined mass. The combined mass therefore must fall vertically. Because no net horizontal linear momentum of the system before and after collision. So vertical. 14 Bombay. Shall we proceed? So now passage 2, the second passage. There is an elevator at a certain instant of time. It has an upward velocity of 10 meters per second. There is a point P on the elevator, inside the elevator, at a distance 1.5 meters from the ground. The floor of the elevator is 50 meters from the ground. At the instant when the velocity is 10 meters per second in the upward direction. The bullet, okay, and there is no roof in the elevator. The bullet strikes the floor of the elevator in 2 seconds, and the initial velocity of the bullet, urel, that means relative to the elevator, is given to be 15 meters. second with respect to the elevator, it's 15 meters per second. And then in 2 seconds, the problem says that the bullet strikes the floor of the elevator. The bullet strikes the floor of the elevator, right? We want to be able to find the acceleration of the elevator in the upward direction. So you can choose to call F the acceleration of the elevator in the upward direction, right? Now let me look at everything in the elevator frame of reference. Let me look at everything in the elevator frame of reference. That means the equivalent scenario is freeze the elevator. This is the point P. With respect to the elevator, it's 15 meters per second upwards. The acceleration of the point P with respect to the elevator would be G, the resultant Gn minus F. G plus F there. G minus F. The acceleration of the point P with respect to the ground minus the acceleration of the elevator with respect to the ground, which is minus. I'm taking downward positive, upward negative. So then, well, it does not matter though, but it's going to be G plus F downwards. It's going to be G plus F downwards. Now, by the time, so now it's as if the elevator is fixed and this bullet is fired with a velocity of 15 meters per second and it has an accelerator G plus F, which means when it hits the floor of the elevator, its displacement must be 1.5 meters downwards. Its displacement must be 1.5 meters. Right. So let's say if I take upward positive, downward negative, to write my equations, upward positive and downward negative, then from P to the ground, the displacement is minus 1.5. From P onto the floor of the elevator, eventually the net displacement is minus 1.5. So minus 1.5 has occurred in 2 seconds. In 2 seconds, because of an initial velocity 15 meters per second minus half of G plus F into 2 squared. Yes or no? I've taken downward negative, is it? No. But when I wrote this equation, see that I was explaining G plus F downwards. G minus F, that gives me G plus F, magnitude downwards. Right? So when I write this equation, I say displacement is minus 1.5 into the, it does not matter. This is the sign of every element here will change. So minus 1.5 is ut minus half G plus F squared. So that gives me 2 times G plus F is 31.5 or 15.75, 5.75. F is 5.75 meters per second squared is the acceleration of the elevator. Right? Clear? Find the displacement of the bullet relative to the ground. In 2 seconds. Displacement of the bullet relative to the ground would be displacement of the bullet relative to the lift plus displacement of the lift with respect to the ground. Yes or no? Displacement of the bullet with respect to the ground would be the algebraic sum of the displacement of the bullet with respect to the lift plus displacement of the lift with respect to the ground. Yes or no? Right? Now again, let me choose upward positive, downward negative. So displacement of the bullet with respect to the lift would be minus 1.5. Displacement of the bullet with respect to the lift is going to be minus 1.5 in 2 seconds. So minus 1.5 plus displacement of the lift with respect to the ground is going to be ut plus half ft squared. Is ut plus half ft squared, where u is 10 meters per second for the lift, right? So the displacement of the lift with respect to the ground is going to be 10 u for the lift. Initial velocity is 10 into 2. And the acceleration is f upwards. So half of f, which is 5.75 into t squared, which is 4. Now whatever this turns out to be, 11.5, 10, 20, 30. This is 11.5 minus 1.5, 10 plus 20. Right? 30 meters is the displacement of the bullet with respect to the ground in 2 seconds by the time it hits the floor of the elevator. Right? Find the maximum height reached by the bullet relative to the ground. Find the maximum height reached by the bullet with respect to the ground. Okay, now with respect to the ground, what is the velocity with respect to the ground? 25 meters per second, yes or no? With respect to the lift, is 15 meters per second, but the lift itself is 10 meters per second. So with respect to the ground, it must be 25 meters per second, right? So then, very clearly, it reaches with respect to the ground, with respect to, let's say, this point, it reaches a maximum height. It reaches a maximum height, h max. This would be u squared by 2g, right? Plus 50 plus 1.5 with respect to the ground, plus 50 plus 1.5, that's the maximum height with respect to the ground. So h max with respect to the ground is going to be u squared by 2g plus 51.5. 50 plus 1.5, right? So which is like 225 divided by 20 plus 51.5. 625, which is 31.25, 51.5, which is 82.75 meters. 82.75. Yes or no? Right? Make sense? The next part of the problem, find the maximum distance between the floor of the elevator and the bullet during its path. So now come back to the relative scenario. Well, maximum height, say as if the lift is fixed, the maximum height above P reached is going to be u rel square divided by g plus n, and then plus 1.5. Lift is fixed, the effective g is g plus n, so maximum height above this is going to be u rel squared by 2 g plus n, u squared by 2 g plus n, and plus 1.5 meters. That's the maximum height above the floor of the elevator, right? Right. So maximum height above the floor of the elevator is going to be 1.5 plus u rel squared divided by 2 times g plus, or whatever this turns out to be. Yes or no? Samrit, square, no? With respect to the floor of the elevator, 1.5 plus another u squared by 2 times g plus f. That's by the elevator. Clear? Hmm? Oh, there is one more part of the problem. Okay, I'll just redraw that. This is where the bullet was launched at P. If the lift did not move, then, or rather, it was launched with a velocity u equal to 25 meters per second with respect to the ground, right? So this must be h equal to u squared by 2t. This must be h equal to u squared by 2t. Now, by the time it reaches P, it would have covered 2h. But then it's prematurely obstructed because of the upward movement of the lift. So let's say this point of the lift, this BB of the lift goes to BB prime, B prime, B prime. Yes or no? So what we'll have is 2h minus this, 2h minus this. Yes or no? So what is this? The upward motion of the lift in 2 seconds is 10 meters per second was the initial velocity. In 2 seconds, t, and plus half of f by 0.75 into 2 squared, right? 11.5 plus 20, 31.5. Yes or no? Right? This is 31.5. So it's going to be 2h minus 31.5 is the distance covered by the bullet. Yes or no? It's going to be, this would have been 2h minus 31.5, where 2h is u squared by 2t. That's the total distance traveled by the bullet. 2h minus 31.5, whatever it is. Right? Shall I move on to the next passage then? Alright. So there are 3 bullets fired from A, B and C simultaneously. B is fired with a velocity u equal to 100 meters per second at an angle of 30 degrees to the horizontal. A is fired at a certain velocity. And when it arrives at O, that is its maximum height. C is fired upward with a velocity of 100 meters per second. Right? And they meet at O. We want to be able to find the time in which the collision occurs. Now this distance is 1500 meters. This distance is 1500 meters. Think of it like this. The collision between B and C, because we have data known for B and C. So let's look at the collision between B and C. It's as if C is fixed, I freeze C and I cause B to collide with C. So if I freeze C and I look at B in light of C, then by the time B reaches C, what's the displacement in the downward direction? 1500 meters, yes or no? What's the displacement in the vertical direction by the time B collides with C? 1500 meters in the equivalent situation where C is frozen and B is allowed to bump into C after a while. See, if I freeze C and I look at B, eventually B would come and collide with C. So in this equivalent situation where C is looked upon as an observer, vertical displacement of B in order that it could collide with C in the equivalent situation is going to be 1500 meters. As if C is fixed, the velocity of B would have to be revised. Realize that the velocity of B is like a u sine 30 degrees like this and a u cos 30 degrees. Right? Now, what causes in the equivalent situation, what's the velocity of B in the vertically downward direction with respect to C? It's going to be u sine 30 degrees minus 100. That means u sine 30 degrees plus 100. So then the velocity of B with respect to C in the downward direction is going to be u plus u sine 30 degrees. U plus u sine 30 degrees would be the relative velocities in the vertical direction, and the displacement accomplished in the equivalent situation is 1500 meters, and the relative acceleration is 0. So the relative velocity in any direction remains preserved, right? So the time taken for the collision is going to be a vertical displacement of 1500 meters caused by a relative vertical velocity of u sine 30 degrees, which is going to be u by 2 plus u 150, and that makes it 10 seconds. U is 100 meters per second, so 10 seconds. So in 10 seconds the collision occurred. The equivalent situation could be used towards calculating the time it takes for the collision. The actual position of B and C here would be, it will not be known, but the time it takes for the collision would be obtained very easily, right? Okay. Now once we know that it takes 10 seconds for B to bump into C at O, of course it takes place at O, evidently, then this distance, the collision actually occurred at O, right? It occurred at O, that means u cos 30 degrees acting for 10 seconds caused this displacement, right? So this must have been caused by u cos 30 degrees acting for 10 seconds. U cos 30 degrees acting for 10 seconds, that means this M2 must have been u cos 30 degrees, means u is 100, cos 30 degrees, root 3 by 2 acting for 10 seconds, which is 500 root 3 must be MO. 500 root 3 must be MO, yes or no? The vertical displacement of C, CO, is U initially upwards for 10 seconds and G downwards. So that makes it 100 into 10 minus 5 into 10 squared. So that makes it 500 meters. CO then is 500 meters, yes or no? This is 500 root 3, sorry, this is 500 root 3. I'm sorry, I wrote 500 root 3 there, and this is 500. Right, this is 500 meters, right? And this angle, 5. This is 500 root 3, and that's 500. So what's tan phi? Tan phi is 1 by root 3. Phi therefore must be 30 degrees. Phi therefore must be 30 degrees. Does it make sense to all of you? Clear now? Find the velocity of the bullet at A. Hey, look. Simple. Both A and C have the same vertical displacement in the same time. Yes or no? They have the same vertical displacement in the same time, and they have had the same vertical acceleration G. Do you then realize that they must have had the same initial vertical velocity? Yes or no? So the initial vertical velocity of A must have been the initial vertical velocity of C. That is 100 meters per second. 100 meters. Right? And in 10 seconds, A must have accomplished a horizontal displacement of 500 root 3. In 10 seconds, A must have accomplished a horizontal displacement of 500 root 3 seconds at a constant rate, because in the horizontal direction, its velocity did not change. So its horizontal velocity of A, the horizontal velocity of A must have been 500 root 3 covered in 10 seconds at a constant rate. Right? So that makes it 50 root 3. Uy is 100 meters per second. So the net velocity of A is going to be 100 squared plus 50 root 3 squared. 10,000 plus 7,500. So 10 root 175. 500. Yeah, so 10 into 25 into 7. So 50 root 7. 50 root 7. 50 root 7 must have been the velocity of A at the instant of launch. At the instant of launch. Yes or no? I hope all of you are comfortable with everything that I've said. Right? Okay, oh, we are done with passage 3. Passage 4. Let's look at passage 4. So far, so good, right? No issues. Clear, no? By the way, do you realize that there was some extraneous data in the problem? Did I at any point of time use that O is the highest point reached by A? So there is unnecessary data given in the problem that was not even required, right? The fact about O being the highest point reached by A was never used to solve the problem. That was redundant, isn't it? Actually, of course, this was not done intentionally in the problem. But I do know in some of my courses at Carnegie Mellon, they would give us problems in which, 100 pieces of data would be given and only 2 would be required. So you had to actually have an eye for the useless data and, set it aside. When someone sets a problem, he's actually defining so many things for you. But when you're actually solving a real life problem, you have to define your data, you'll have umpteen data around you and you will have to pick and feed the data. So that's scientific thinking, right? So you would actually have to, over a period of time, learn to rubbish some data, take some data, and use that data. Okay. There was a particle that moved parallel to the x-axis with a constant acceleration, start from rest. Right. A projectile launch, let's say with an initial ux and a u1, and by the time the projectile reached this point, it hit the particle B. 1 second later, it hit the particle B. Now we want to be able to find the acceleration of B. We want to be able to find the acceleration of B, given that the height at which the collision occurred was 2 meters, and it occurred 1 second later. Evidently, then realize that from B to B prime, the displacement of B horizontally is half of A into T squared. Half of A into T squared. And that must also have been the horizontal displacement of A in 1 second. That must have been equal to the horizontal displacement of A in 1 second. So that must have been ux into 1. Horizontally, it's unaccelerated. A is unaccelerated. It moves with a constant velocity ux horizontal, right? Which means I need to know the value of ux. I need to be knowing the value of ux. Now, one thing, ux at A is the same as ux at this point. That is not true. Also realize that at this point, since this is 45 degrees, this is 45 degrees, realize that this velocity must be the same as this velocity in magnitude. So if this was ux, the vertical velocity must have been ux downwards. Yes or no? That means 1 second later, the vertical velocity changes from uy to minus ux. 1 second later, the vertical velocity changes from uy to minus ux. Yes or no? So that means 1 second later, we have the final vertical velocity ux equals initial vertical velocity, which is uy, right, minus gt So minus 10, 10 into 1, right? Also, in 1 second, the vertical displacement is 2 meters. Yeah? Wait, in 1 second, the vertical displacement is 2 meters for it. Yes or no? So 2 meters is cos by 2y acting for 1 second minus half gt squared. So minus 5 into 1 squared. So that gives me uy equal to 7. That gives me uy equal to 7 meters per second. And if uy is 7, ux is 3. All of it. This equation for particle A, displacement in the upward direction in 1 second is plus 2 meters. 2 meters is initial vertical velocity into t minus half a, that means half g, which is 5 into t. I have written the displacement in 1 second equation for the displacement in 1 second. Upward positive, downward negative. So 3 equals ut plus half at squared, a is minus b. No? I'll explain again. So that gives me uy equal to 7 meters per second. So uy is 7, I get ux at 3 meters per second. And if ux is 3 meters per second, a must be 6 meters per second squared. Right? Now, very clearly, bb prime is like ux acting for 1 second. bb prime is like ux acting for 1 second. So bb prime is 3 meters. Do you realize that bb prime is 3 meters? It's 3 meters per second. In 1 second, the horizontal displacement would be 3 meters. So bb prime I know is 3 meters. Now, if the acceleration of the ball B is 4 meters per second squared, part 24, this was what I did was 23, now 24. If acceleration of ball B is 4 meters per second squared, and the ball A still strikes after 1 second, the ball A still strikes after 1 second. Now, in 1 second, at the rate of 4 meters per second squared acceleration, B would have covered 2 meters. Half of 4 into 1. Half of 4 into 1 squared. That means B at time t equal to 0 must have been at B double prime. And it would have covered half of 4, which is 2 meters. It would have covered 2 meters. B would have covered 2 meters. Yes or no? That means at time t equal to 0, B must have been here. At time t equal to 0, when A was launched, B must have been here. And this point, therefore, must be 1 meter from the y-axis, because this whole thing was 3 meters. So the x-coordinate of this point must have been 1 meter. The x-coordinate of the particle B at time t equal to 0 must have been 1 meter. In order that, with an acceleration of 4 meters per second squared, it could still be struck by A at the same location. See, the acceleration of B is 4 meters per second squared, and the ball is still strikes after 1 second. Right? So now if the acceleration is 4 meters per second squared, then in 1 second, what's the displacement of B? 2 meters. So this is at t equal to 1. So at t equal to 0, it must have been 2 meters away from here. That means at t equal to 0, B must have been here, 2 meters away. So that in 1 second it could reach this point. And therefore, if since the entire length BB prime is 3 meters, the x coordinate of B at time t equal to 0 in problem 24 must have been 1. Find the velocity of ball A at the instant of launch, obviously. At the instant of launch, the velocity of ball A must have been ux I cap plus uy j cap. That means 3i plus 7j. 3i plus 7j must have been the velocity of ball A when it was launched. Right?